So as we talked about, organic chemistry is really the study of carbon and carbon-based molecules. The basic sort of organic molecule really has a carbon backbone where carbons are essentially attached to carbons. And usually attached to those carbons are a number of hydrogens. And this is usually involving all non-metal and non-metal interaction. So we're sharing electrons here all the way around. And a couple of things about normally these kind of basic organic bonds. Most of them are non-polar bonds. And again, definitely the carbon-carbon bond and the carbon-hydrogen bond are all non-polar bonds. And that gives organic compounds some different properties, including because overall they're non-polar in most cases, they usually have very low melting point. Because of that, they oftentimes will be a lot of early organic molecules or gases because they're not held together very tightly. And they're usually insoluble in water, basic organic molecules. As we talked about along the way here, and as we'll see as we go through these different chapters, some of these hydrogens will be replaced by other elements like oxygen, nitrogen, some of the halogens in group 7. And as we sort of replace some of these hydrogens with other elements, we do make a different type of organic compound. And there's kind of different classes of organic compounds, and they differ by what is sometimes referred to as their functional group. And the functional group is really the part of the organic molecule that's different than another organic molecule. It's also kind of the main part of the compound. It's sort of the active part of the compound. And because it has whatever is that particular functional group, is what makes it a certain type of organic compound. We started with really the simplest and basic organic compounds that you could have, and those are alkanes. And alkanes, really, the functional group is the carbon-carbon single bond. They are all single bonded together. They have a general form of CnH2n plus 2. And basically, if you know how many carbons, they'll tell you how many hydrogens it should have. And as we talked about, really important in sort of your organic journey is understanding and learning those first 10 alkane names and formulas, as pretty much everything goes back to those kind of names. So everything falls back to those names in terms of how we name things. So again, if you have 1 carbon, you will have 4 hydrogens. 2 times 2 is 1 plus 2 is 4, and that is methane. If you have 2 carbons, you will have 6 hydrogens, and that is ethane. You have 3 carbons, that is 8 hydrogens, that is propane. 4 carbons, 10 hydrogens, that is butane. 5 carbons, 12 hydrogens, that is pentane. 6 carbons, 14 hydrogens, that is hexane. 7 carbons, 16 hydrogens, that is heptane. 8 carbons, 18 hydrogens, that is octane. 9 carbons, 20 hydrogens is nonane. And decane is 10 carbons and 22 hydrogens is decane. These are all alkanes, which ends in ane, and every single one of these names basically ends in ane. And that's how you know you're dealing with an alkane, and you're also dealing with everything should be single bonded. When we talk about hydrocarbons, that's sort of what I drew up there on top. A saturated hydrocarbon, which we also talked about, is basically a molecule where they pretty much have all single bonds. And that means that what ends up happening with our carbon is it has the maximum number of hydrogens that it should have. And that happens with all single bonds. And that's what happens here. That's a saturated hydrocarbon. All the carbons have the maximum number of hydrogens that they should have. Other important thing, speaking of carbon and its bonds, remember carbon is a 4-bond situation. And that's always a good thing to keep in mind as you're drawing these things. You do not want to end up with 1,000 bonds to carbon or anything like that. Also important to remember that when you're kind of done drawing like we were towards the end, and you have nothing left to put on your picture, everything else can be hydrogen to get carbon to 4 bonds, and it'll kind of help you understand how many hydrogens you should add to do that. We talked about a couple different types of sort of formulas. This sort of formula here, where you can really draw it out like a true sort of Lewis structure, is sometimes referred to as the expanded structural formula. And it really is just sort of drawn out, and you draw out all the bonds along the way. There is sort of a shorthand formula for that, and that is what's known as the condensed formula, where we could write CH3, and that is what that represents, attached to a CH2, which is what that is, attached to another CH2, which is where that is, and attached to a CH3, which is what we got going on at the end there. And that is what is referred to as the condensed formula, or condensed structural formula. And really the main difference there is we just really don't draw out the hydrogens or anything like that. When you do see sort of the connection here, just so you should keep in mind, in a condensed formula, it may appear that the connection is between the hydrogen and the carbon, but it is not. It is, as you can see on the top there, it's always carbon to carbon, hydrogen always on the outside. But in a condensed formula, it may appear that the connection is between those two. Is not supposed to be that way, and it's not implied that they're connected that way. It's just implied that that carbon has 2 hydrogens. We also talked about line structure or line formula, which is really your bare basic sort of formula where you basically just use lines, and everywhere sort of the line ends, or everywhere where the lines kind of come together, represents a carbon, and the proper number of hydrogens is assumed to be there. And this is sometimes referred to as line structure. And again, that's a carbon. Once again, that's a carbon, that's a carbon, and that is a carbon. So everywhere I put a circle represents basically a carbon. We got into a couple of things, including naming and isomers as well last time. And just to remind us that we can have isomers, which are basically has the same molecular formula, but some different connectivity. And so I think maybe we looked at butane, I think. And here, this is C4H10. We could also have this guy here, where maybe we do this. This is also, if you count it up, C4H10 in this case. So once again, they both do have the exact same formulas, and they are isomers of each other. And as we talked about last time, really the best way to determine whether or not, again, something is an isomer, or if you're asked to draw an isomer, is to actually name it. And if you do come up with different names for whatever you drew or whatever was drawn for you, you probably do have isomers as long as they have the same molecular formula. If you come up with the same name, it is the same compound, just drawn differently. So the rules to name a compound is we always look for the longest carbon chain. And remember, you may have multiple sort of options as to how to count that. And it may not always be the one that just goes straight across. And, may start down, come up and over, or something like that. So you do want to, as we went through some of those examples last time, want to kind of check all of your sort of options and see whichever one has the longest. When you do, that really will hopefully match one of those 10 alkane names that we talked about a second ago. And that will really kind of be like the base of your name. Then we typically have stuff that is not part of the longest carbon chain. And those are what are sometimes referred to as groups. And if they are carbon-based groups, they're referred to as alkyl groups, which again is a fancy way of saying a carbon-based group. And you would then want to really kind of identify any groups that are present. Hydrogen is not really considered a group when naming, but any group that is present that is not part of the longest chain, and you want to name those. And remember what basically most alkyl groups, which are carbon-based groups, they are basically based on uh, the alkane names as well. So, and how many carbons you have. So remember that if we have something like this, which is 1 carbon and 4 hydrogens, that is methane. Now, as we talked about last time, if I wanted to kind of hook methane up into a carbon chain, I really can't do it at this point because carbon already has 4 bonds to it. So basically, these alkyl groups are pretty identical to the alkane. The only difference is they are missing 1 hydrogen. And because they're missing 1 hydrogen, that gives them an opportunity to bind into the chain and not have too many bonds. So basically, our alkyl group here will look exactly like methane, except it is missing that 4th hydrogen. And because it's missing, again, that 4th hydrogen, that is the place where it's able to kind of connect in and not give carbon too many bonds. We name it the same way. The only difference is we drop the last part of the name. And because this is an alkyl group with a YL on it, instead of this being methane on the right, this now becomes a methyl group. And again, basically named the same way. And then if you had a 2 carbon group, it would be an ethyl group, propyl group, and so forth. Now, when we talk about groups, and we'll see it a little bit later, it does depend. There are some groups that have some different sort of names. And just to talk about it here, let's just talk about, I'll talk about that in just a second, actually. But we have our group name. And the next thing we want to do is once we identify all our groups, we want to number the longest carbon chain. And usually when you go to number the longest carbon chain, you basically have 2 options to do that. You can kind of either go left to right or right to left or up and down, whichever way you're going. And the goal in terms of numbering when you're naming alkanes is to give the groups that are attached the smallest numbers. So it's always like the smallest number when you're naming in organic chemistry. And that's sort of the goal here, is to give the groups the smallest number. And once you've done that, you've identified your groups, you identified what carbons they're on, you can now name it, and you go with your groups in alphabetical order. And that is regardless of prefix. So for example, I think we saw one at the very end where it's like dimethyl or something like that. And we would not look at the di part of the name there. And a couple just finishing points when we do that, and obviously the base of your name at the end. Wherever we go from a number to a letter, we put a dash between them. Whenever we go from a letter to a number, we also put a dash between the 2 things. And whenever we go and have basically 2 back-to-back numbers, we put a comma between the 2 numbers as well. So these are like the little sort of finer points there at the end. So again, to kind of go through this is obviously 4 carbons straight across. There's really nothing else there. So this is butane. Again, if we were going to look at the guy here on the right, our longest carbon chain is 3, and you could get that by, again, going straight across, or you could go halfway through and go up. It will also give you 3. And 3 in this case is based off of propane. We also have a group attached, which is a 1 carbon group, which is a methyl group. And again, to number this, we could number 1, 2, 3. In this particular case, we could also go 1, 2, 3 in the other direction. And really, and this happens sometimes, it doesn't really matter which way you go. This group is bond number 2, no matter which way you go. So 2 is the number there. And that's really the entire name there. We just kind of put it together, and it's going to be 2-methyl propane would be the name of this. And because those two things do have different names, they are isomers of each other. They have the exact same molecular formula, and they are two different compounds because they have different connectivity. First off, any questions on that there? Last thing we talked about at the very end is drawing these from a name. And remember that when you draw from a name, you basically want to work backwards in the name. So you want to kind of go right to left. By doing so, that'll tell you basically how many carbons to put there. And then you basically keep going to the left, and it'll tell you where to put all your groups. And then anything left over at that point will be hydrogens to get everybody to 4 bonds, all the carbons to 4 bonds, and then you get there. Any questions on any of that there? All right, so we're speaking a little bit about groups, and we're going to see that a little bit here in a second. But just to also talk a little bit about another kind of idea of alkanes is when we have carbons, we could actually classify the carbons in one of 3 ways, and they typically are classified as a primary carbon, a secondary carbon, or a tertiary carbon, and they are sometimes identified by that. How do you identify if it's a primary, secondary, or tertiary carbon? Probably the easiest way to do is this. You just look at the carbon you're interested in. We'll just go with this guy. And basically, all you have to do is figure out how many carbons are directly attached to it. So in this case, there is 1 carbon directly attached to it. 1 means that carbon right there is a primary carbon, and because it has 1 carbon attached to it. By the way, the carbon with the arrow on the left-hand side would be what type of carbon? That one would also be a primary carbon because it has 1 carbon attached to it on the other side, right? So both of these carbons are primary carbons. They both have 1 carbon directly attached to the carbon you're looking at. If we look at something like this, let's do it this way maybe. If I were to look at this center atom, would that be a primary, secondary, or tertiary carbon? It would be a secondary because directly attached to it is 1 carbon there and 1 carbon there, and that would be a secondary carbon. Yeah. I just to save space, to be honest with you. Yeah. So you could, I didn't feel like drawing out the hydrogens, but you could draw out the hydrogen. Obviously, the hydrogens there on the outside are all connected to the carbon. Yeah. Just like you. So in this case, it's a secondary. How about the carbons there with the arrows? What are those? Yeah, they're both primaries again. The guy on the left is attached to obviously the carbon in the middle directly, and the guy on the right is also attached to the carbon in the middle. So in this case, we have 2 primary carbons in this compound and a secondary carbon in this compound. And again, if we did something like this, what would the carbon in the middle be? It would be a tertiary carbon, again, because it has 1, 2, and 3 carbons attached to it. All the outside carbons would be primary carbons as well, because they're all individually attached to the guy in the center as well. Now, here you can see a couple different ways that sometimes you'll see people write this. Sometimes people will kind of write the CH3 like this, where it kind of shows the carbon being attached, and sometimes people will write it most likely like I just did there, where it kind of looks like the hydrogen attached. But remember here, the connectivity is this. So even though it may appear in a condensed formula that the carbon's attached to the hydrogens are on the outside, and it is the carbon that's attached to the carbon. Any questions on that there? Well, what's that? It may be both ways, to be truthfully honest with you. So most likely it'll probably be like this, I would say, but sometimes it may appear that way in some cases. And some books will do that too sometimes, stuff like that now. Just to try to avoid, sometimes books will do it like that to try to avoid the people thinking like the hydrogen and carbon are attached to each other and stuff like that. So why do I bring up primary, secondary, and tertiary? It's an important thing in organic chemistry. We can sort of classify carbons that way as we go through other sort of organic compounds. We can also classify, for example, alcohols as primary, secondary, and tertiary, and other things as well. But it also plays into those groups. And sometimes it is possible that you may have a group that has the same number of carbons, but we'll end up with a different name for the group because of where it attaches to the main chain. So the most common one, and probably the only one you'll mainly come across in this class, is our friend here. So this right here is a group, right? And how many carbons does this group have? And 3 carbons is what alkane? That is propane. But because this is missing a hydrogen, it is a group, so it is a propyl group, yeah. So it's a normal propyl group. Where the attachment of this group into the compound is going to happen here. The attachment of this guy will happen at this end. And by the way, that carbon where it's going to attach is going to be what type of carbon? Primary, secondary, or tertiary carbon? This carbon right here is a, how many carbons are directly attached to it? 1. So that is a primary carbon, yeah. So a normal propyl group, or just a propyl group is sometimes called, can attach at the primary carbon. It can actually attach to the ring at any of these locations. These are all kind of primary locations. And even on this side, which is also a primary carbon as well. So instead of attaching on the right-hand side, it could attach using the left-hand side where it's missing a hydrogen. Obviously, there'd be a hydrogen on the other side if it did that. Now, because propane has not only primary carbons, it also has this carbon in the middle right here, which is what type of carbon? That would be a secondary carbon. It has the ability to attach at the secondary carbon location to a group. And it could attach right here, obviously, to the ring. This is still 3 carbons, which is still propyl. But this is a special group which is known as isopropyl. It's an historical name that's been used a lot. Maybe you heard of isopropyl alcohol. Yes, that's the deal right there. You put an OH where that little circle is, and you have isopropyl alcohol. So isopropyl is sort of a historical name that's used in organic chemistry for a long, long time, and people still use it. And I would say in this class, that's probably the one that you would maybe come across. It has kind of some weird name. And it usually in sort of condensed formula kind of looks like this. You usually have this type of move. You usually have like this kind of group kind of hanging there in condensed formula if it's a group written like that, kind of a CH3, CH3, CH, CH3 type group. In line structure, it looks like this. It almost looks like, that type of thing is actually an isopropyl group. And it's sort of a line structure type of thing. That's your CH3, your CH, and then your CH3 happening there. And this is where it would connect into a chain or something like that on the bottom part of it. So isopropyl happens because the connection happens at the secondary carbon rather than a primary carbon. There are other ones like butane. There is a sec-butyl group. Sec means that it attaches at the secondary carbon. There's actually a T-butyl group, which means it attaches at the tertiary carbon. So there are some other groups that you probably won't come across too much in here at all, but definitely this one does pop up a lot. So you just want to be kind of familiar with that. It is not just a regular propyl group. It's a kind of a special type of group that is there. Any questions on that there? All right. So why don't you give this one a name here, see what you come up with. Okay, let's take a look. So again, always want to start at the longest carbon chain. So it usually never hurts just to go straight across. So that is 1, 2, 3, and 4, and 5, and learn how to count, I suppose, is good as well. That's 5 carbons. Other options really, which is not going to really pan out good in terms of longest, is you could start here and go 1, 2, 3, and 4, which is obviously less than 5. You could do the same thing on the other side. You'll end up the same. So it does look like 5 is our longest continuous carbon chain. Remember that when you are counting that, as we talked about last time, you can't kind of go backwards. You got to go one way to hit a dead end, basically, and you can't back up and go in another direction. So because it is 5 carbons, that means the base of my name should be pentane, right? Because it's all single bonded, 5 carbons. Base of my name is going to be pentane. We then have some groups that are hanging out there. We have a Cl, and we also have a 1 carbon group. Let's start with the 1 carbon group. That is a methyl group, right? Based off of methane. Now, chlorine here, I don't know if we talked about it or not. Chlorine is a halogen there, right? On the periodic table, group 7. And how halogens are named is you kind of name them like this. If it's fluorine, it's a fluoral group. If it's chlorine, it's a chloral group. If it's bromine, it's a bromol group. If it's iodine, it's an iodo group. So you're kind of like a O-ish on the end of it. So chlorine here is not chlorine in organic chemistry. This is known as a chloral group. And that is, again, how you kind of name those halogens. Chloral, bromol, iodo for iodine, and fluoral for fluorine when you go down there. Any questions so far on that there? So we got our groups, we got our longest carbon chain. Now we need to number it. And remember, you always, when you have the longest carbon chain, have 2 options of numbering. You could go, in this case, left to right. When we're numbering the carbons, 1, 2, 3, 4, and 5. Our other option, obviously, here is to go right to left. And if we did that, this would be carbon 1, this would be carbon 2, this would be carbon 3, this would be carbon 4, and this would be carbon 5. So the goal here, again, when we're numbering, is to get the smallest numbers. So if I go left to right, kind of the black numbering there, I would have groups at carbon number 2 and group at carbon number 3, right? If I kind of went left to right. If I go right to left in the blue numbering, I would have a group at carbon number 3 and a group at carbon number 4. It is, again, as simple as which one is the lower number. Is 2 lower than 3? It is. That's not a trick question. All right, so 2 is less than 3. So we would not want to go this way because that's going to give us bigger numbers, and we want to give the groups the smaller numbers. So the proper way of numbering this would be going from left to right. So we'll get rid of these, as this is not the right way to number it. Get rid of it. Now we actually know our locations of everybody. We know that the chlorine here is at carbon number 2, and the methyl is at carbon number 3. So now that we have basically all of our parts, all we have to do is put it together in alphabetical order. Alphabetical order for our groups is the chloral should come first. So that is 2 chloral dash 3 methyl and a pentane. I don't run out of room there at the end there, pentane. Again, a dash between a number and a letter, a dash between a letter and a number, and a dash again between a number and a letter here. So again, in between basically numbers and letters, you should have a dash to kind of separate them. Any questions on that? As we talked about last time, essentially naming is all about just basically telling people where you can find everything on the carbon chain. Do you have a question? Okay. All right, let's then talk about, I did. I jumped the wrong way there. Let's go look this way here. Let's talk a little bit about cycloalkanes, which we touched upon last time. Cycloalkanes are really kind of like the straight chain where the ends just come together and they kind of close into a ring type structure. And they are also just really based off of the alkanes as well. How we name cycloalkanes is we pretty much just put cyclo in front of the alkane name. So you basically go cyclo in front of the alkane name. Most of these cycloalkanes are usually drawn in line structure. So these are kind of like your geometrical shapes. You got like a triangle, you got like a square, you got like a 5-member type ring, you got like a 6-member type ring. This is again 1, 2, and 3 carbons. 3 carbons is based off of propane. And because it's a ring type structure, this is known as cyclopropane. This is a ring structure where we have basically 1, 2, 3, and 4 carbons. 4 carbons is based off of butane because it's this ring type structure. This is known as cyclobutane. Right? Here we have 1, 2, 3, 4, and 5 carbons, all in a ring type structure, closed type structure. And 5 is pentane. This would be cyclopentane. And finally, over here, 1, 2, 3, 4, 5, and 6 carbons. Again, 6 carbons is hexane, and that would give us cyclohexane here. So if it is sort of a closed type structure that's all single bonded, it's still an alkane, but it's referred to as a cycloalkane. Now, one of the consequences of closing the ring and kind of bringing both ends together is you actually, one of the things you should learn in organic chemistry is pretty much as we might have talked about last time, every time you lay up a bond, you got to get rid of 2 hydrogens. Otherwise, somebody's going to have too many bonds there. So what happens is cycloalkanes have a general form of CnH2n. And for example, if we take a look at cyclopropane, it has 3 carbons and it has only 6 hydrogens. And there it is drawn in the condensed formula down here. 2 hydrogens, 4 hydrogens, and 6 hydrogens there. Each of these guys will have 2 hydrogens coming off here. So all these cycloalkanes will have 2 less hydrogens than the straight chain alkane, and that again is a consequence of the 2 carbons coming together to close it up. It's got to get rid of 2 hydrogens to make room for that bond to basically occur. Questions on that there? Now, here's those guys. So what happens if we had, do it here. What happens if we had, do this. What if we had an actual group there? We'll just do this. Yeah. So if we had a group up here on a cycloalkane, we basically follow the same sort of path as the other way, which is clearly the cycloalkane is always going to be your longest carbon chain. So if you got like a cycloalkane there, it's going to be the biggest and longest carbon chain. So that's a little different than the kind of straight one where you got to count it. So that has 1 carbon here, 2 carbons here, 3 carbons, 4 carbons, 5 carbons, 6 carbons. So that is a closed structure, which should be cyclohexane. Yeah. It also has a group attached, which is a chloral group. And this would be chloral cyclohexane. Now, you may be asking, do I need a number for this? And the answer is you do not in this situation need a number. The reason you do not need a number is there's only 1 group attached, and wherever that group is attached is assumed to be carbon number 1. So if you have just 1 group attached to any cycloalkane, you do not need to give the location of where it's at because it's assumed wherever it's at is going to be carbon number 1 because that's where you would start numbering. Just like if I drew it like this, that is still chlorocyclohexane, and my carbon number 1 would be actually here in this case. That's the same thing, just rotated around basically and stuff like that. So You do not need an actual number for a group in a cycloalkane if there's just one. But if there happens to be maybe two, and let's just say we had that, and we'll do that there. So now when I look at this, I do have again my longest carbon chain, which once again is my cycloalkane. It's this guy, right? That is my longest chain. And that is still going to be cyclohexane. Again, because it has 6 carbons. I do have 2 groups attached. This group here is a 2 carbon group, which is called what? It is a ethyl group based off of ethane because it has 2 carbons. What's that? No, it's actually just an ethyl group because there's just 2 carbons attached to it. So that's basically what ethane looks like, with one less hydrogen, basically. Yeah. Now, how about this one, which is just a lonely line? What is that? It is what? I believe anyway. What did you say? It does end with YL. And what's at the end of that line if there's nothing drawn there? Yeah, it is a carbon, remember. So again, if there's nothing drawn there, that is actually a carbon. And because there's only one line going into it, that carbon would need 3 hydrogens. So that is actually a methyl group. So remember, if you have just a single line drawn and nothing written there, or if you erase the line as well, that's good. But if you have just a single line drawn there, at the end should be a carbon. And remember that that carbon needs the appropriate number of hydrogens to get the 4. So it has one line coming in and would need obviously 3 hydrogens. And that means that this line by itself with nothing at the end of it really is a methyl group like we saw before, right? A 1 carbon group. So remember, sometimes you will see that just like a line, nothing at the end of it. And that again is always a methyl group. If it is something else, like here, they will write what is at the end of it, like they want it to be a chlorine or something like that. They'll put something actually there. So again, just an empty line means it's a methyl group. So now we have a methyl and an ethyl. We actually have 2 different groups here. And in this case, we do actually need to give some numbers. So we do have a couple of options maybe as to what we can do. And we have to number the ring in this case. So we have 2 options, which is we can number going clockwise, 1 and 2. And by the way, we do want to give everybody the smallest number, and going clockwise in this case will do that. By the way, if you went counterclockwise, you obviously are hitting much larger numbers, right, as you go around the long way and stuff like that. So you wouldn't want to really probably number counterclockwise in this case, because it definitely will put that second group at carbon number 6, which is not so great, right? So you will definitely want to go clockwise in this case. And in this case, I started with the methyl. My other option is I could actually start with the ethyl and go counterclockwise to the methyl group. Now, they both end up with numbers at 1 and 2, right, regardless of which way you go. So if I went clockwise in this case, I end up with a number at 1 and 2. If I go counterclockwise starting at the ethyl, I also end up with 1 and 2. The difference here is there is no difference in the numbering. So the next most important thing in terms of order is alphabetical, right? And if we were going to put these group in alphabetical order, which one should come first? The ethyl group should come first, right? E before M, right? And because E should come before M and there is no difference in terms of the numbers, we most likely would actually want a number and give the ethyl group the smaller number. So alphabetically, our smaller number will have our guy will have the smaller number. So we probably want to go 1 ethyl, and this would be 2 methyl. And now we could put it all together, 1 ethyl, 2 methyl, I lost now, cyclohexane. Any questions on that? So sometimes there is a tie in numbering, and sometimes it doesn't really make a difference. And sometimes what you want to do is always think about kind of what's the most important thing. And in the case of alkanes, it's the group locations. And if it happens to be a tie for the group location numbers, the next most important thing is alphabetical. So you then want to go, okay, which one is alphabetical, and give that person the smaller number than the other one. Any questions on that there? All right. So why don't we just make, let's just do that, and let's just add a few things here to this one to fancy it up a little bit, maybe. Let's do that, and let's do that. All right, give the name of that. Why don't you also draw something? Let's see. Why don't we draw like, you draw 2 bromo, 3 chloral. I'm running out of room. I'll go underneath it. Butane. All right, so name my, let's take a look, see how you're doing. Again, we're gonna start with A. We're looking for the longest carbon chain. Might as well just check straight across. So I got 1, 2, 3, 4, 5, 6, 7, and 8. That's probably looking pretty good. We do maybe want to check some other options. So we could also go here and go 1, 2, 3, 4, 5, 6, 7. That's close, but still less than 8. We also could have went 1, 2, 3, 4, 5, 6, also less than 8. So it does look like the straight across one there of 8 is a winner. I'm going to try to erase that without erasing everything there. There we go. All right, so with 8 carbons as the base of our name, all single bonded, obviously here, that base of the name should be octane, right? ANE for 8. We do have some groups there. We have a bromine group, which is a bromol group, right? And how many carbons is this thing? This is a 2 carbon group. 1 carbon there, 2 carbons there, right? Just drawn in line structure. And 2 carbons is ethane, and since it's a group, it is a ethyl group. Yeah. So again, we got our groups hashed out. Any questions on that so far? Yeah. You, if you're asking, do you count this carbon for the group? You do not, because you counted that as part of the longest carbon chain. Yeah. Otherwise, you're kind of be double counting the same carbon. Yeah. Other questions? Yeah. So yeah, so this would be an ethyl. A methyl really in sort of line structure will really just look like the line. It would just be like a line like that. So, if this was a group, that would be what a methyl group would look like in line structure. Yeah. It would look, I'll draw one right here. It would look just like this. Maybe if I draw it, it would just look like that. Yeah. And that is the 1 carbon, 2 carbon, and 3 carbon right there. Again, we wouldn't count the carbon on the bottom there because that's part of the main chain and stuff like that. And that would give to you that carbon in the middle has 3 lines coming to it. So that's the CH part of the middle part. And the 2 ends would be the CH3s and that. All right, let me take my isopropyl off of here. Yes. Okay. So now we need to number, right? So again, we have a couple options. We could go this way: 1, 2, 3, 4, 5, 6, 7, and 8. We obviously could go in the other direction. So if we go this way, I'll go red with this. 1, 2, 3, go 4 right there for that carbon. 5, 6, 7, and 8. Going in the red direction, we have a group at carbon number 4 and 5, right? And kind of going in the blue direction, left to right there, we have a group at carbon number 4 and 5 in this case, right? So once again, it is a tie no matter which way you go. Which way should I go in this case? Red or blue? So the numbers are tied, right? So the next important thing is alphabetical, right? So between the groups, right? So which one should come first alphabetically? The bromo, right? B before E. So we would want to, again, in this case, because the numbering happens to be a tie, which you can see does occur occasionally, we would want to go in this direction because, again, that's going to give alphabetically the guy the smaller number. So that is the way we will go in this case, and that means that's going to be a 4 bromo there, right? And that will be a 5 ethyl. And that's pretty much all we need for the name now. We can put it together here. We'll go alphabetical there. 4 bromo dash 5 ethyl, and then octane. Not bad, just adding stuff to it, I suppose. Didn't mess it up too bad, I suppose. Now, speaking of this naming and stuff like this, here's also something that does confuse people sometimes. It is definitely possible that when you go do your numbering, you could end up alphabetically, the one that should come first will end up with a higher number than the next alphabetical guy. So that's okay. So as long as you go alphabetical, it is okay in some cases that that guy ends up with a higher number than the next guy. As long as the numbering you numbered from lowest, kind of order in that situation. So that does sometimes occur. So it's possible you could have like a 5 bromo, 2 ethyl type thing. And as long as that compound, the numbering was done correctly, that's possible that could happen as well. Yeah. So, it is. So that's what those numbers represent, if that's what you're asking, like the 4 and the 5. Basically, what you're saying when you name this is if you go to carbon number, if you go to carbon number 4, you should find a bromine there. And if we go 1, 2, 3, and 4, there's a bromine there. And if you go to carbon number 5, 1, 2, 3, 4, and 5 right there, you should have an ethyl group hanging out there. And again, that's what those numbers mean. And that's what the 5 means. So it's basically the carbon location of where you can find those groups. So, other questions? And that carbon at number 5 is part of the longest chain. So it is not, again, counted as part of the group carbon. So, other questions on that there? All right, taking a look at this one here. Obviously, we got a cycloalkane happening. So that is going to be our biggest carbon chain. And that's going to be a 1, 2, 3, 4, and 5. So 5 is based off of pentane. And because it's a ring type structure, we just add cyclo to the front of it. And that means that we do have a group right there, and that's just a blank line, which means that blank line is a methyl group. Again, there's a carbon at the end of it. And in this particular case, because that's the only group attached here, we don't, again, need the number. So this is just going to be, I'll try to squeeze it in here at an angle, methyl cyclopentane in this case. Any questions on that one there? All right, lastly here on this one, we're going to draw. So always want to work backwards. So we want to draw 2 bromo, 3 chloral butane. So first off, butane tells me how many carbons should I draw? I think I heard 4. Yes, so 4 is how many carbons butane has. So remember, when you're drawing it, that's basically what you want to start with. And you can kind of cross that off. Now, remember, as we talked about last time, because you are drawing it, it's your choice as to where you call carbon number 1. You could call the carbon on the left number 1, the carbon on the right number 1. For me, I'm going to call this guy right here number 1, my carbon number 1. But you could just as easily, if you wanted to, call the carbon on the right-hand side your number 1 because you're drawing it. So whichever one you want to call number 1, it's up to you. But you got to keep consistent in, like, if that's number 1 on the right, then I got to go right to left in my numbering and so forth. So that means at carbon number 3, I should find a chloral group, which is a chlorine. And for me, my carbon number 3 would be right there, and I should have a chlorine hanging out there. And now at carbon number 2, I should have a bromine hanging out right there. And now I'm out of names because I scratched it all out. So whatever is left at this point is going to be hydrogen. And again, remember the goal of the hydrogen here is to get carbon to have 4 bonds. So my carbon on the right-hand side here has this one line coming in, which means in order for it to get to 4 bonds, it needs 3 hydrogens. My carbon next to it has 1 line, 2 lines, and still 3 lines coming in. And that means to get to 4, it needs just 1 hydrogen, right? Carbon next to it, similar deal. It's got 1 line, 2 lines, and 3 lines, which means it needs 1 hydrogen. And lastly, the carbon on the left here, my carbon number 1, has only 1 line coming in, which means it would need 3 hydrogens in this case. And now we are done. What I just drew there is what type of formula? That is the condensed formula. That's what I just drew there, right? I didn't draw out the hydrogens. If I wanted to do line structure, it works the same way. You just start with the carbons. So you could just zigzag yourself 1, 2, 3, and 4 carbons. And once again, you could choose whichever side you want to be carbon number 1. So I'll choose that side. That means my carbon number 3 would be here. I would draw a line with the chlorine, and my carbon number 2 would be here, and I would draw a line with the bromine. And since it's line structure, we never put the hydrogens in, so you're done at that point, which would be the line structure in this case, yeah. Yeah, so you could draw any structure you want unless it specifically says like, hey, draw the condensed structure or draw the expanded structure. Or if it gives you any type of direction, you technically should draw whatever it asks you to draw. But I'd probably be happy with any structure you lay up there that looks good. Yes. Any questions on that there? All right, let that digest for 5 minutes, come back and we'll continue. Yes. Okay, let's take a look. So when you're drawing isomers, remember as we talked about, they should have the exact same formulas, exact same number of carbons and hydrogens in this case, and they should end up with different names. So obviously here, the first isomer is just the simplest, hopefully. Perhaps we should just go 5 across, right? Seems good. And at that point, I'm just going to add the appropriate number of hydrogens. So the guy at the end needs 3 to get the 4 bonds. The guy next to him needs 2 hydrogens to get the 4 bonds. Needs 2 hydrogens to get the 4 bonds. 2 hydrogens to get the 4 bonds. And 3. And that should give me 3, 5, 7, 9, and 12 hydrogens. So that definitely is C5H12. Now, where do I go from there? Well, maybe I don't do 5 in a row, but how about 4 in a row? Yeah. And maybe I throw a carbon over there, and now I finish it up. Put 3 hydrogens there. He will need 2. Just needs 1 as he has 3 lines coming in. Just needs 3 and also needs 3. Again, counting up, I have 4 carbons. I have 3, 6, 9, 10, 11, 12 hydrogens. So that's looking good. All right, well, I went 5, 4, 3. Seems like the next number is less than that, right? So maybe I go 3 in a row. And maybe I put a carbon here, maybe a carbon there. And now I add my hydrogens. So I need 3 on that outside one. I need 3 on that outside one. I need 3 on that outside one. And I need 3 on that outside one. Guy in the center already has 4 bonds, so he has no hydrogens. And I have 12 hydrogens and 4 carbons, or 5 carbons in this case. Well, how else can I maybe do a 3? Can I go 3? I'll go here and maybe go there and there. And if I do my carbon or hydrogens, 3 there, 2 there, 2 there. I'll squeeze my 2 in there and squeeze my 3 in there. So 3, 2 is 5, 7, 9, 12. All right, there's a bunch of options. So we want to make sure that our options are good. And again, that's a good way to draw isomers. Start with just a straight one, then drop down straight number of carbons, drop down straight number of carbons, move things carbons around. All right, so this first one here, if you put H's all around, I'm sorry, I don't understand. H's all around. If you just drew out the H's, is that what we're talking about? Like, are you asking, would it be wrong if you kind of drew out the hydrogens like that? Is that what you're asking, or yeah, yeah, no, it's fine. It's just a different formula. What I drew here again is the condensed formula, just kind of saves some space. That would be more again the expanded structural formula if you wanted to. So, and sometimes it may look a little bit more crowded with all those hydrogens, which is why sometimes people won't kind of draw that formula a lot because it gets really crowded really quickly and stuff like that. But it wouldn't be necessarily wrong in this case. Yeah. Which one? This one? If it writes that one right there where I'm magically writing nothing, sorry, again. Are you talking about this one? Yeah. So the deal with isomers is not that it needs to be 5 carbons in a row. It needs to have the same number of carbons and the same number of hydrogens in each one. So if you count up the carbons and hydrogens in each one of those pictures that I drew, they all have 5 carbons and they all have 12 hydrogens. And that potentially makes them all isomers of each other. Yeah. So an isomer doesn't mean just the same picture over and over. Otherwise, you're basically just drawing the same compound, right, over and over again, right? So it doesn't have to have those in a row. Again, an isomer just basically means in this case, when you look at the number of carbons and the number of hydrogens, or if there's any other elements involved, they all have the exact same numbers of each of them in that case. Correct. And actually, you don't usually want it. Otherwise, you basically kind of just drew the same thing over and over again. Basically, it may just look different. So that's how we want to really check ourselves too, is we do want to go back here and name these just to make sure we didn't accidentally draw the same thing twice, right? So obviously here, our longest carbon chain on our first one I drew is just straight 5 across. Nothing else is there. So clearly the name of this guy is pentane, right? So that's a good start. Longest carbon chain with the one on the arrow on the bottom left there is how many? Longest carbon chain is 4. 1, 2, 3, and 4. By the way, you could also get 4 going this direction as well. It doesn't really matter. I would just take the straight one. So with 4 as our longest carbon chain, that means the base of my name for this one is not going to be pentane, but is going to be butane, right? And I have a group now that's hanging off there, which is a methyl group, right? And if I had to number that, which way should I go to give it the smallest number? Yeah, 1, 2, 3, 4. That's going to give that methyl group a smaller number. If I went the other way, obviously it would end up at number 3. And that means that the name of this guy is 2-methyl butane, yes? Both of those guys have 5 carbons and 12 hydrogens. They both have different names. Congratulations, those are isomers, yes? If I ended up with the same name, not so much an isomer, right? So those are 2 isomers of each other. Let's go up here on top. Longest carbon chain up on top is how many? It is 3, and you can get that a variety of ways. You go straight across. You can actually go up and down if you want. But 3 is our longest carbon chain. 3 carbons in a row is propane. So that's a good start for isomers because that's definitely a different name. Question? Great. For this type of question, it'd probably be worded very similar to this, like draw as, for example, in lab, probably you have a question like that as well, like draw as many isomers of, and they give you a formula basically, and that would be how it would be asked for. If you weren't asked to draw any isomers and you're just asked to, hey, draw the structure of C5H12, you could lay up any one you want, basically, that is C5 and H12, basically. There, yeah. So here are groups now, is a methyl group there, right, and a methyl group there. By the way, that is not just one methyl group in this compound, but that's 2. So my methyl group now becomes a dimethyl because there's 2 of them in the compound, right? If you have 3 of them, it'll be a trimethyl. If you had 4 of them, it'll be a tetramethyl and so forth. So the di, again, and just to remind you here, does not mean that they are necessarily on the same carbon, which they happen to be in this case. It just means in that compound, there's 2 methyl groups. They could be on the same carbon. They could be on different carbons. The prefix is just telling you there's multiples of the same group in that compound. And again, could be on the same one or different ones. I need to number this. I'm going to go right to left here. 1, 2, 3. Doesn't really matter. It doesn't, right? Because those groups are going to both end up at carbon number 2. And even though they're both on the same carbon, you do need to give the number twice. So this is a situation where we go 2 and a comma, 2 and a dash to indicate that each of those methyl groups are on carbon number 2. So this would be 2,2-dimethyl propane. Each 2 represents that at carbon number 2 of the longest chain, you should find a methyl group basically hanging out there. Yeah. Any questions on that there? So clearly a different name. So is that another isomer? That is another isomer. So I got 3 of them. Look, I did extra work. Let's see if I did extra work or not. Maybe I didn't. Longest carbon chain on the one here on the right is 4. Any more than that? 5. It is 5, actually. 1, 2, 3, 4, and 5. Nothing else there other than the 5, which means the name of this guy is pentane. Yeah. Did I draw another isomer? No, I just made it look different, right? This structure here and this structure here are the same. And that's a common error people make, as I mentioned maybe last time. They're like, I'll just like move the end down and like move the other end up and it looks all fancy, but it's actually the same molecule in this case. So this is actually not a 4th isomer. This is the same thing as the first guy. So here, there's 3 isomers of it in that case. And as I mentioned before, if you need to draw isomers, that's a really good way to do it. If you have like 6 carbons, just start with 6 in the head, straight across, and then drop down 1 to 5, and then move one of those carbons in away from the end. That's the important thing. Don't put it at the end. Otherwise, you just make what I did at the end there. You got to move in from the end carbon when you do that. Drop another carbon, move in from the end, and put the carbons in those spaces. And you usually end up with pretty good isomers. Now, there was a question earlier about, can you draw maybe like a cyclic structure? And the answer is you're not going to be able to do that in this case, because what happens if I draw this, which is 1, 2, 3, 4, and 5 carbons, how many hydrogens does that have? It has only 10, right? Because this needs 2 hydrogens here. This needs 2 hydrogens here. This has 2 hydrogens. This has 2 hydrogens. And this has 2 hydrogens. So although this has 5 carbons, because I had to close it into a ring, I have to sacrifice 2 hydrogens. So this would not be an isomer, obviously, of this, because it does not have the same formula. That would be C5H10. So a lot of times, if you have something like this and there's definitely an alkane, you can't kind of close it up into a ring because you will sacrifice 2 hydrogens and end up with something that doesn't have the same sort of formula. Question on that now. Yeah. Okay. Say again? Are you going to have for like a group or something? Is they're asking? Yeah, you could. And again, they just go off of the alkane name. So if you have 3 carbons, it would be propyl, butyl, and so forth. So they're really based off of, again, those first 10 names. So potentially you could have up to 10. I don't know if I'd ever give you that, but 10, potentially they could go up there. Was that? Probably not. I always think, uh, yes, now that you said no, we're going to have it all day. Yes. Um, just a long chain of 400. I don't know. But no, I don't know. I mean, I'm not going to say it's only going to be methyl and ethyl, but definitely probably methyl, ethyl, butyl, propyl, those are common. Probably not high up into like, 7, 8, or 9 or anything like that. Yeah. Yeah. No, I mean, you would have like we've been doing in some of these examples a name, and you have to draw it would be most likely what you would have to do. Yeah. And again, in terms of isomers, I don't know there'll be a heck of a lot of questions on it, other than you'll come across probably some in homework and stuff like that. But if you were asked to draw an isomer, it would say in there, hey, draw 2 isomers of this or something like that. And in terms of groups, you can have groups that could go anywhere through those 1 through 10s. But I will tell you, as you get into those higher group numbers, or numbers for the groups, is sometimes what happens is those groups then become part of the longest carbon chain, so they're actually not a group, and you end up with smaller sort of groups that usually happens and stuff like that. Here is a table from your book, again, of some of those groups that we talked about, and as I mentioned before, here's our isopropyl group, which is a CH3, CH, CH3, and as I mentioned, there's also a butyl relationship of it, which is isobutyl. But I think for us, isopropyl is probably the most complicated group that you'll come across, other than obviously this the regular methyl, ethyl, propyl, butyl type of group, pentyl type of groups. All right, so that's what we talked about before. All right, so we did that. All right, so why don't we draw this one here, 3-bromol, 1-chloral butane. Okay, so as we've talked about previously, always want to work backwards when you have the name given to you. So butane once again tells us that is just 4 carbons in a row. So that is where you should start. Takes care of that. I'm going to call this my first carbon. So at carbon number 1, there's actually a chloral group, which is a chlorine. So that takes care of that. And over here at carbon number 3 for me would be a bromol group, which would be Br over in that area. And now again, everything at this point is going to be hydrogens to get carbon to 4. So at the end here, it needs 3 to get to 4 bonds. This carbon next to him has 3 bonds already, so just needs 1. Carbon next to it has 2 bonds, so to get to 4, you need 2. Guy at the end has 2 coming in, so you need 2. And that would be our condensed formula in this case. First off, any questions on that? And then write the hydrogens. All right. So earlier I was talking about it is possible that you could have a bigger number first in alphabetical order. So this is an example of that. Here we have obviously a larger number for our alphabetical one, and that's perfectly fine, and that does happen. Line structure, once again, just going to start with the zigzag move, 1, 2, 3, and 4. Again, I'm going to call this my carbon number 1 over here. So at carbon number 1, I should have a chlorine. And I do need to put the Cl there, otherwise if I just leave it as a line, I just added another carbon to my drawing, which I don't want to do. And at carbon number 3, which would be right about there, we're going to do a bromine in that case. Yeah. Any questions on that there? Question on drawing or naming alkanes? All right, so we kind of did all these examples there. We talked a little about some of the properties of alkanes, and again, because they are basically carbons and hydrogens and nonpolar, a lot of the early alkanes, methane, ethane, propane, butane, are typically going to be gases at room temperature because they're held together by these really weak forces. As you get to 5 to 8, they are highly volatile liquids. And again, volatile means that they could go into the gas phase really easily. Just open the bottle and they'll just kind of go into the gas phase and stuff like that. And as we get into longer and longer carbon chains, we're making sort of petroleum type products, which again are basically long chains of carbons and hydrogens. And as they break them down into smaller chains, they make other things like parafilms, waxes, motor oil, and so forth. As we also talked about, because they are nonpolar, again, they typically are going to be insoluble in water because water wants to use hydrogen bonding and water is polar. So again, that idea of like dissolves like. So something that is nonpolar, like a alkane that's organic, is not going to mix well with something that is polar, that is like water. You would need something that's also an organic to sort of mix with it. So if you took an organic compound, you took something like hexane or heptane and mixed it together, they would mix because they're both pretty much non-polar, so they would mix together. Now, let's talk about a couple of types of reactions that alkanes undergo. They undergo one that we've seen before, which is a combustion reaction. So an organic compound that contains carbon, hydrogen, and oxygen, or oxygen, has O2 and will make CO2 plus water. That is the same reaction we saw when we talked about types of reactions. And that is pretty much the reaction that happens when you light up the Bunsen burner there. Methane plus some oxygen in the air, a little bit of spark, and you get fire, and will always produce CO2 and water. So in a combustion reaction, those are, especially an organic combustion reaction, those are the three that are almost a constant. O2 on the left-hand side, and it always kind of produces CO2 and water. It is possible to produce carbon monoxide in a incomplete combustion reaction, but usually CO2 and water is what you see there on the right-hand side. Now, another type of reaction that alkanes undergo is what is referred to, find a space there, is what is referred to as a substitution reaction. And basically in organic chemistry, there's substitution reactions and there's addition reactions. And in a substitution reaction, what happens is one thing goes off and somebody comes on into their place. So alkanes can basically replace, if you will, a hydrogen. So you can take any one of these hydrogens, and if you add something like chlorine to it, what will happen in this reaction is a chlorine will come on, and this guy will come off. And one of the things you should learn really quickly about drawing products of reactions in organic chemistry is don't get fancy with it. Yeah, and the structure that it starts with and the structure it ends with is pretty much the same thing, just a very small part of it changes. So for example here, this is the only part that changes. So if I want to draw what I get, I'm just going to copy what's there. So nothing is going to change other than the part that does change. So pretty much this entire part of the molecule stays the same. Nothing happens to it. And what happens here is a substitution reaction, which means I'm going to throw a chlorine on here. And that leaves one chlorine that's by itself and a hydrogen that comes off. And those two guys come together to make HCl. And this is a substitution reaction. This is what is known as a monosubstituted product. A fancy way of saying just remove one hydrogen, basically. You could actually, in this case, take any hydrogen you like on there and change it out for a chlorine. They're all the same. So you could actually replace any of those hydrogens in this type of reaction. So an alkane will basically just do a substitution reaction. Hydrogen goes off, like a halogen comes on, a chlorine or a bromine comes on in its place. Everything else remains exactly the same. So even if you had like a ring type structure, it is not saturated here because it doesn't have the maximum number of hydrogens, basically. Yeah. So usually saturation will kind of really refer to having the maximum number of hydrogens in this case. Yeah. So in this case, there's hydrogens here, and if you did the same reaction, works the same way. That goes off. This comes on, and nothing else changes other than we put a chlorine on there, and we end up with the same thing. So this is a basic sort of reaction that an alkane can do, which is a substitution reaction, and basically take a hydrogen off and put somebody else on. Any questions on that there? Okay. So the next thing we're going to talk about here is another two types of organic compounds, which are alkenes and alkanes. And alkenes have a functional group of the carbon-carbon double bond, so they have at least one double bond. Alkynes have a carbon-carbon triple bond, and that is the functional group for each of those. Now, as I might have touched upon earlier, as we do these double bonds and triple bonds, we end up, again, losing some hydrogens to make room for that bond that's coming on. So if we look at sort of a comparison of an alkene, an alkane, and an alkyne, we could actually do that by, if I find somewhere here. I'll do it here. So if we have this guy here, which is an alkane, we'll draw out the hydrogens in this case. This is 2 carbons, which is ethane, A-N-E. Now, again, as we might have touched upon last time, if I wanted to double bond my carbon in the middle, I can't just put the double bond, otherwise carbon will have too many bonds to it. So we do actually lose 1 hydrogen from each carbon where we insert a double bond. And if we did that, we will end up with a double bond, and we will lose 1 hydrogen on each of the carbons in this case. Again, that allows carbon not to have too many bonds. And this is an alkane over here, A-N-E. This is an alkene, E-N-E. And the name of this is ethene, E-N-E. Again, based on the number of carbons, which is ethane. And if I go in triple bond now, I have to remove 2 more hydrogens, 1 from each carbon, and I will be left with just 1 hydrogen on each carbon. And this is now an alkyne, which is known as ethyne, Y-N-E, just like the ending of the name. In case shit missed out there. So again, they are each related to the alkane by the number of carbons. These are what are referred to as being unsaturated, to your question. Here, they will not have the maximum number of hydrogens because of the 2 that are lost every time you make a double bond or a triple bond, the alkene and the alkyne in this case. Now, an alkene has a general formula of CnH2n because it loses 2 hydrogens when it makes the double bond. An alkyne has a general formula of CnH2n minus 2 because, again, it also has to lose 2 more hydrogens to make that triple bond. And a reminder, as we've been talking about, an alkane, which is all single bonds, is CnH2n plus 2. Again, those are the general formulas. Now, just to finish up on here for today, just to kind of touch upon this, let's talk about how we kind of name these when we have more than a couple of carbons happening here. So if we have something like this, and we'll just do our double bond right there, and maybe we'll put 1 more there. H3. H3. So here, first off, we can identify this as an alkene. And we can identify it as an alkene because obviously we have a double bond happening right there. So this is an alkene. Now, the rules of naming this is the same deal. We're still looking for the longest carbon chain. The one exception is here, we need to make sure that the double bond is part of it. So you can't miss the double bond. You have to find the longest carbon chain that has a double bond and also the longest carbon chain that has the triple bond. So you can't just kind of avoid those 2 things. So in this case, we're just going straight across, right, in this particular case. And how many carbons do we got there? 1, 2, 3, 4, 5. So 5 carbons is based off of pentane, but because it has a triple bond, we replace the back end of this, and this now becomes pentene because it has a double bond, E-N-E. Now, what happens when you get to about 3 or more carbons, when you have a double bond or a triple bond? The priority in terms of numbering goes to always, in this case, the double bond or the triple bond. So if you remember when we numbered the chain, the priority went to the groups. When you get to a double bond or a triple bond, the priority in the numbering is to give the double bond or triple bond the smallest number. And when you get to 3 or more carbons, you will have an opportunity where the double bond or triple bond could be in different locations. So you actually have to give the location of where that triple bond or double bond is located. So in this particular case, which way should I number to give that double bond the smallest number? Left to right. 1, 2, 3, 4, and 5. Obviously, if I went in the other direction, I'm looking at a double bond at carbon number 3, but going left to right, my carbon double bond starts at carbon number 2. So we do have to give the location of where this double bond is located, and this would be known as 2-pentene. The 2 is telling where the double bond is located. Not a group, just where the double bond is located. First off, any questions on that? And it would work the same way if you had a triple bond. You would have to give the location of where the triple bond is located. Now, when you do that, and I'll leave my double bond there perhaps, and I'll throw a bromine right there. So again, my longest carbon chain is still going to be this, right? Which is 5. Still has the double bond, which is pentene. Right? Now again, I have a group, which is a bromol group, right? And I also, again, have the double bond. Once again, in this situation, the double bond is the priority, which means we will still number this the same way. We're going to number it this way to give the double bond the smaller number. I don't care about the group so much at this point. Again, double bond comes first. The only time I will care about the group is it doesn't make a difference for the double bond. You get the same number. Then you should think about the groups as going small. Now, because of that, this is still 2-pentene. And because I had a number this way because of the double bond, that locks into place where my group has to be. They have to use the same numbering for the group. So that means the bromine will end up at carbon number 4, right? And this would be just like the other kind named 4-bromol dash 2-pentene. Yeah. 2 is where the double bond's located. The 4 is where the bromine is located on the carbon chain. And again, the numbering is based off of the double bond. And again, if you had a triple bond, same deal. It would be based off of the triple bond. Any questions on that there? No. Again, for the one that we did before, which was ethene or ethine, there's only one location where that double bond could be between the two, so you don't have to give the numbering. So usually around 3 or 4 carbons, you got to start including the number of the double bond or triple bond, and again, it takes the priority there in terms of numbering. Any questions on that there? All right, one last one here to call it a day. What would you name this thing? I don't know either. I just drew it. What is the longest carbon chain? We think we work it together since we're at the end. What is the longest carbon chain? I think so. 1, 2, 3, 4. That sounds good. So if we go straight across, we got 4, right? So 4 is based off of butane, but in this case, I have a triple bond, which means instead of ANE, it should becomes butyne. That is the triple bond, the YNE, right? ENE double bond, YNE triple bond, ANE single bond, right? All right. I want to number this. Which way should I number it? Yeah, again, we want to give the triple bond the smallest number, so definitely doing that. It's going to put it at the smallest number. So this is now going to be 1-pentene because of the triple bond location. And because I had to go in that direction, that means the chlorine is going to end up at carbon number 3. So that's going to be a 3-chloral 1-pentene. Yeah. Any questions on that there? So again, I'm hoping you can see a pattern that everything goes back to those first 10 alkanes. So as I mentioned last time, get a handle on those first 10 is going to make everything else super easier as you go through the different groups. Yeah. All right, we're laid up there for today.